Hey, it's Brevin with Brev Engineering. A project I've been really interested in is a 3D scanner. Being able to take any small object and obtain a 3D reconstruction of it or basic geometry in a virtual environment is just super useful an idea to me. But I really want a 3D scanner because when you have difficult shapes that are hard to make by hand, or you want to repair something that's broken in the house, or just want to edit a cool item you have in the house and add some kind of crazy feature to it or take something away, it'd be really nice to have just a scanner you can put that on so you don't have to go through and make the whole part yourself. I actually already tried to make a 3D scanner once with like a turntable design. Didn't work out super well. But back then, that was 3 or 4 years ago, I didn't know a lot about mechatronics or robotics. Definitely did not know computer vision, and programming wasn't my strong suit. So I just made a glorified paperweight. I'm determined that I'm an older boy now, and I know how to make one that works. In this video, we'll talk about how these 3D scanners work. There's a lot of them. They're very popular. We see them all over the market now. And how the idea behind a 3D scanner, why a 3D scanner. This includes both the hardware, the electronics, and the software. I'll talk about the math and the physics of the scanner and also the algorithms that make this work. We'll be ending up using OpenCV, so we're not going to be designing a photogrammetry package by hand, but I will talk about how they work. And then in later videos, I will show how I make this whole scanner, and hopefully we'll have a functioning prototype. So first, let's talk about some of the most popular kind of forms of 3D scanners. You have laser depth, which calculates the time of flight. So you have almost like an ultrasonic or an IR sensor that has a light sensor that detects, or sound sensor that detects, the distance between the travel time of the light or the sound when it hits an object. You have stereo vision that reconstructs through depth maps. They tend to not work super well because stereo cameras that are nice, very expensive, and don't do well with plain surfaces. What I'm going to be doing is photogrammetry, which is where they take thousands or hundreds of images and of an object at all different angles and locations, and through some computer vision algorithms, they reconstruct a 3D model. And then there are others, but these are the main ones that I'm familiar with that we'll be kind of touching on. They also have different hardware designs. So a very popular one is a turntable kind of design. That's what I originally was thinking of doing, at least with my old project, where you would have a disc that spins the object, and you would just have a camera that's fixed that takes pictures of the object as it moves on the turntable. And maybe the camera can move up or down, but mostly it's just moving the object around on a turntable. But there's an issue with this kind of design in that a huge problem with photogrammetry algorithms is they're not very good at discerning an object under different lighting conditions. So if you rotate an object and the light bulb is staying the same, then the lighting on the object has changed. So it has a hard time inferring if looking at one side of the object is different than looking at another side of the object, because the lighting is identical, but the surface has changed. So instead, a better way to approach this that I want to try is to use a camera that moves instead of having a turntable that moves. So you'll be working on a kind of a rack and pinion sort of two degree of freedom gear system that suspends a camera that moves up and around the object while the object stays in the same lighting. Yeah, we'll go through the hardware of how I plan to do that, and the mechatronics, and some other design considerations to optimize the computer vision and just the software component of this too. So yeah, let's jump in. Let me show you how this works. All right, let's talk first hardware design. So as I mentioned before, I want to do kind of a camera movement version instead of a turntable. We're going to be using a phone. I just want to use my phone camera to do this because I think that that's accessible. Most people have phones if they want to use this design. All right, so let's say that we have an object sitting on a platform. Let's make it an apple. Right here, sitting on a platform. What we're going to do is we're going to suspend this platform up somehow, and then we're going to have a big ring that goes around this object. So circular. This will be a gear. A big, long gear. And on this gear, it's an internal gear, I should mention, so the teeth will be on the inside. You'll be able to suspend a phone somehow. So this is like a clamp that would hold the phone, or a camera, any camera would do. So we'll say that this is our camera. It's like an eye. And this can see the object at all points here. Now, this ring can rotate with some motor gear system. That'll be down here. So this will have the freedom to move this way and this way. And then we also want to be able to spin around this apple, this object, to get the other field of view from it. So we can go around, but we also need to be able to see all the other side. So we will add another motor down here that spins around. So we have these 2 degrees of freedom. Let's talk about the algorithm for computer vision. So we'll talk about photogrammetry. I think that's how you spell it. Don't double check me there. The process of taking images and reconstructing a 3D object. So Python has a number of libraries, but we'll talk about each step. So the first step is to take your pictures with a camera, and then you'll load them in. You'll use those to refer to different points on the object, and then the algorithm will detect the points on the object and create a 3D model from that. But how does all that happen? Well, first we got to talk about camera calibration. So camera calibration. And there's 2 sides to this. So your camera inherently sees what it's got. It's got a lens on it and a focal length to determine, what's in focus. And then because of the lens design, you'll have distortion where parts of the image are pushed or pulled a little bit. It's not really easy to see, but it can cause errors in length measurements. So we have to calibrate the camera, and we do that with 2 steps. So there's an intrinsic step and an extrinsic step. Intrinsic calibration tells us about the camera itself, the focal length, any distortion parameters within the camera. Extrinsic tells us relative to the world. What is the camera seeing? How far is the camera from this chalkboard? Is this 1 foot, 2 feet relative to here? That's what we learn. And we do it in we can do these in kind of the same step. A really common way of doing this is to take pictures from several angles of a checkerboard or chessboard, and you can use algorithms that detect edges of the checkerboard or the chessboard. Right? So we detect the edges or the corners of those pieces, and it's able to determine, hey, well, a checkerboard or a chessboard will have a fixed square size. We'll say like it's 1 inch. Then we know from whatever angle we see, no matter where the camera is positioned, the distortion and the orientation of this checkerboard will allow for us to calibrate the images according to what the real world size should be, because we know these boxes are 1 inch. That will give us these matrices that allow us to calibrate our camera. Okay, so what does that actually look like? Well, we'll get these matrices. Intrinsic, we have a 3x4 matrix where we have the focal length X, focal length Y, followed by 2 zeros. And we also have offsets or distortion coefficients, sigma X, sigma Y. It looks like this. And this is determined just by the physics of your camera. Best done if you leave it to the algorithm to solve for these. This is the intrinsic matrix. We call this one sometimes like KI, or different versions of seeing the different letters for that. Extrinsic is similar, except for it's a homogeneous transform, which means it's a 4x4 matrix that describes a point and orientation in 3D space. Simply put, it has this form. We have the first 3 columns describe the orientation or the rotation of the object in 3D space, and then the last column describes the position. So I call these just by the row names. The bottom row is all 0 except for the last one's 1. This is just a homogeneous form. If you're interested in that, look up homogeneous frame transformation. And so this tells you the orientation and position of the camera relative to some spot in 3D space. So when you look at a checkerboard, oftentimes the algorithms will parse a checkerboard's corners according to the top right or top left inner corner, and that will tell you relative to wherever the camera is in 3D space where that thinks that point is. So that'll be this position and this orientation relative to that point. Oh, by the way, the extrinsic matrix is called KE, like the intrinsic was KI. Okay, so you're probably asking, what does the camera calibration have to do now? Like, what are we going to do with those matrices? How's that helpful to us? Like, we know the position, but great, how do I use that to determine what the 3D object looks like? Because you can't just do that for every point in an image and just assume that the next image that you take will recognize that. But the great thing is, say we had the camera here, and we took an image of, this is the camera, what it's seeing. It sees an object out here, and it sees a dot on the object. Well, then we have the camera, we've moved it over here now. So this is camera 1, and this is camera 2. This is the object, and it sees this. Well, we have the calibration intrinsic matrix, which should not change for the camera ever. And the extrinsic matrix, which really shouldn't change either, but we also know the world positions of these cameras relative to some checkerboard that we had used to calibrate the camera. And now we replace the checkerboard location with an object, so that the camera is looking around this area where we anticipate to do our scanning. And from this angle, you're looking through this camera at the object. You see a point here of the object, which translates to a point in 3D space. There, we draw a line. And we do the same thing and we see that object over here, right there, that point at least of the object. So we've drawn 2 lines, and the thing is we have 3 points. And now 3 points define a plane in 3D space. So there's a line here that exists that we call the epipolar line. Or the plane, the epipolar plane. And this is useful because it helps us relate one point in an object to the other point seen in an image, 2 different images, which we can use to kind of reconstruct our 3D geometry as we move across the model. So what we're going to do is we're going to first, the algorithm here is to find what this epipolar plane is. And by pulling out this epipolar plane, we're able to determine something called the essential matrix. And what the essential matrix does is it allows us to determine points in one camera frame relative to another camera frame. So if I had a point here, and then I took an image, if I was to determine that I can see this point in this image, then I'd be able to determine where this point in this image would be theoretically with the essential matrix. So we're going to derive the essential matrix, and then we can show you how to use that with Python's OpenCV to generate a photogrammetry model, and also with Open3D or PCL to create a 3D point cloud of the actual object. So the epipolar line. So what the first step is knowing what the line normal to this plane is. We define a plane by its normal line. And that equation here is defined as, this is, if we call this one xt, and if we call this one xr, these lines, and then we can call the transform from C to C1, which was the KE, which is described by a rotation and a translation vector, right, which we had in the homogeneous matrix, the R columns and then the T column. Then we can get the normal vector right here, N, call it big N, is equal to this translation vector from C1 to C2. Call that T, or just T, crossed by either of these vectors. I'll use xt. Cross product, if you don't remember, is a linear algebra term that helps us determine perpendicular lines in 3D space. A few things we know is that we can use a dot product as well between 2 lines. And if the dot product between 2 lines, if their 2 lines are perpendicular to each other, then we also know that the resultant dot product is 0. If this isn't making sense, I'll leave a link to some linear algebra stuff that'll help us find this derivation a little bit better. So the dot product of x of t times this cross product here should be equal to 0. So we have x of t, right? And we're dotting that with the result of the cross product of the normal plane. So n dotted with x of t, which should be normal to each other in 3D space, is equal to 0. The whole point of this, right, is to help us make some constraints that you'll see when we solve this that help us derive this essential matrix. What we're going to do here is, now that we kind of defined that one constraint, the epipolar constraint is what it's called. It's when you have the line on the polar plane crossed with the normal, or crossed with, with the normal, and then you dot that. It should equal 0 because it's a perpendicular line. So if you were to write this cross product out in matrix form, you could get something that looks like this. But one of the things that we know that's going to be useful here is how to relate the point in the left image to the right image. Is we know that we have that homogeneous transform from before, the extrinsic property, right? So we could say that the left image, I've been using a T, I should have used an L. It's kind of confusing because these are transforms right here. Those are not the same small t as the big T. Let's just continue using small t to mean the left image and a small r for the right image. Is that we can relate the points in the left image, x, y, and z, to the points in the right image from the homogeneous transformation matrix. If we were to multiply the point in the left image by transformation in the right image, then we would get this, we'll say we put KE here, times the point in the right image should be equal to, so we'll do the rotation part of the point times the position of the point in the right image, all of that plus the point in the translation to the right image in x, y, and z. And these t's up here reference the translation from left to right. If you add that over there, this gives us what we know this point to be. So what we can do is we can substitute this expression for this, and I'll show you what that does for us. Okay, so I have the example of the original equation substituted with the transformation from left to right in for the original expression here. What we can look at here is we focus on this. When we have the skew-symmetric version of a cross product, you can look that up in linear algebra, skew-symmetric times the point of the line itself. You have two lines that are on top of each other. It's just equal to 0. Then we can get rid of this part, and we're just left with this part up here, which is what we call the essential matrix. So when you have the cross product of the position times the rotation times the point we're going towards, then we can make these substitution for what we call the essential matrix to relate 2 points to each other. So we often just call this E, 2, 3, E, 3, 3. Doesn't really matter. You don't need to remember the specifics of all of this. This was just to give you an idea of what we're doing if you cared about the math. So if you had the point in image left times this essential matrix, you get point in image right. So that's how the epipolar constraint is useful. Why does any of this matter? Well, for photogrammetry, you're doing this hundreds to thousands of times in order to construct a 3D object. Another thing that we do is we use something called SIFT. And I'll insert what the abbreviation is here. But SIFT, I'm not going to get into this algorithm much, but let's say you had an image that has some shapes on it, square, triangle, circle, and then you had a similar image, the same object in the image, but from a very skewed perspective, where the triangle and the circle and the square look very different. The SIFT is really good about detecting features that are present in different images. So it will look for critical changes, whether it's color or edges, and segment out these easy to define features of an image. And then it'll look into another image and decide, based on probability, most likely what the correct orientation of your image is and where those features line up here, right? And if it sees enough similarities, it'll know the relationship between the two. And it does that by predicting the probability of this feature based on this size, based on how recognizable it is to the same thing in that image over there. You should look up SIFT if you want to learn about how that works more. So in 3D scanning, what happens is you take a bunch of images, it runs SIFT over all of the images, it detects similarities between points in the object, and since we already know the essential matrix, we know what the 3D points that we're looking at are on all of these objects for every image relative to each other. And with those tools, knowing you construct a point cloud. That's how a 3D scanner works on the mathematical level. Now doing that in code, I'll show you how to do that in the next few videos. I'll show you how to CAD up the hardware to make this possible. I will also show you how to design the Mechatronics system and wire that all together, and how to program that so that it will run automatically and take the images for you in the next few videos. If you like this, like and subscribe. If you have any comments or concerns, if you went through something too fast, if you can't see something, or you'd rather not get into the mathematical details of it, let me know, and I'll focus on some of those other things that might be more fun or interesting for you guys.